Hello, welcome to my talk on Panna method for fluid structure interaction, part 3, boundary integral equation for 2D flows. In 2D potential flow, we don't have the boundary integral equations as in the 3D flows. This is a real case for fluid dynamics. It is more difficult to obtain the boundary integral equation in 2D flows than in 3D flows. So in this talk, I will first show the beautiful mathematical derivations to obtain the boundary integral equation in 3D flows, and then the difficulties why we can't obtain the boundary integral equation for 2D flows as we have in 3D flows. In this talk, I will give a brief introduction of 3D boundary integral equation on how we can obtain the boundary integral equation for 3D flows. And then we will see the differences of the boundary integral equations for the 2D and the 3D flows. Then I will introduce the 2D Panna method for the potential flows and how to obtain the 2D boundary integral equation. And last, I will give an example. A uniform flow past a circle in the 2D potential flow to see how we can solve the 2D potential flow using the Panna method. In 3D, the desingularization on the structure surface SB would lead to a boundary integral equation given as this. Here, on the left-hand side, the potential phi is on the boundary SB, and the integral of this function would be on the control surface SC and the body surface SB. If we write this integral into two parts, we have the equation as this. Here, the potential phi is still on the boundary SB, and this part is the integral on the body surface, and we assumed the desingularization is on this surface, thus there will be a gap on SB, see here. And this part, there will be no gap, thus SC would be a complete surface. And in 3D flows, the integral on the control surface, this part, can be easily transformed to the value on the body surface SB. See the next slide. Now in this slide, we will see how we can transform the integral of this on SC to the value on SB. Use the superposition method. The potential function phi can be decomposed as phi 0, the potential function for the uniform flow, and the phi star is the potential flow due to the distribution of the source on the structure. Thus, we can separate this integral into this, the integral on the potential phi star, and the integral on the potential phi 0. Since in 3D, the potential due to the distribution on the structure would be roughly proportional to 1 over r. Thus, its normal gradient would be roughly proportional to the inverse of r squared. This is the same for this normal differentiation. So if we consider this for this integral, we can see the integrand would be proportional to 1 over r cubic, while the surface integral would be roughly proportional to 4 pi r squared. Thus, the limit when r is infinite, then the integration would be 0. Thus, this term is 0. Then for the second integral on SC, we can assume the flow enclosed by SC only, and phi 0 is the potential flow for the uniform flow. Then we can desynchronize to obtain the potential in the flow enclosed by SC. Here, phi 0 is the potential function on SB. We can assume SB is in the fluid enclosed by SC somewhere here. This is the equation transforming the integral on SC to the value on SB, and thus the boundary integral equation on SB can be established as this. Here, the potential function phi and the potential function phi 0 are all on SB, and the integral is on SB as well. So this boundary integral equation is the boundary integral equation on SB only. Now we have a look on the desynchronized Green's theorem for 2D flows. As I have shown before, the desynchronization in the fluid for 2D flow would be given as this. Here, in 2D, the potential function phi 0 would be given as logarithm r. So this is the equation for desynchronization in the fluid, and the phi here is the potential in fluid. And on the 2D boundary, the desynchronization equation would be given as this. Here, the potential function phi is on the fluid boundary, see here. Now, we suppose a 2D structure like this CB in a uniform flow U0. Then we can make a large circle C as the control curve, and the fluid domain S would be enclosed by C plus CB. So the total potential function phi can be decomposed as phi equaling phi 0 plus phi star. Phi 0 is the potential function for the uniform flow, and phi star is the disturbance potential function due to the existence of the structure in the uniform flow. Since the structure can be represented by distributing the source on the structure on the body curve CB, and the disturbance potential function would be given as phi star proportional to logarithm r, and the normal gradient of phi star would be proportional to 1 over r, and the same for the normal gradient of ln r is proportional to 1 over r. So this means at infinity, if the control curve is very large, the disturbance velocity V star would be proportional to 1 over r. It would vanish when r is large enough. Hence, at infinity, the uniform flow is only taken, even though the existence of the structure CB here, or we have the expression as this when r is infinite. Now we look at the boundary integral equation for 2D flow. This is the equation by desynchronized on the boundary, either on CB or on C. But here, we are concentrating on the desynchronization on the structure surface CB. Thus, we can take the potential on the left-hand side, phi here on the boundary CB. And we can write the integral into two parts. The boundary integral equation can be expressed as this. Here again, this potential function is on the boundary CB. This part is the integral on CB. And we can see there will be a gap on CB here because of the desynchronization. While this integral on the control surface C, there will be no gap, and this curve integration would be a complete curve. Then we need to convert the surface integration on C to the value on CB, as we have done in 3D case. But can we do this as we have done in 3D case? This is a big question. Now we look at the integral on the control curve C as this. Use the potential function decomposition. We can split the integral into two parts. The part on the disturbance potential function phi star and the integral on the potential function phi 0 for the uniform flow. As we have shown, the disturbance potential function would be proportional to ln r. Thus, on C, the normal gradient of the disturbance potential function would be roughly proportional to 1 over r, and this is the same for this normal gradient. Thus, the integral for this term, we can see the integrand would be proportional to 1 over r ln r, but the integral on the whole curve would be proportional to 2 pi r. And time this together, it would be given as this, and it would roughly proportional to ln r. So when r is infinite, this value would not be 0. Instead, it would be a very large value. That means in 2D flows, we don't have the similar boundary integral equation as we have seen in 3D flows. Then we may have a question how we can solve the 2D potential flow problem. Generally, we have many different ways for dealing with the 2D potential flow, or more specifically, the 2D panel method. In here, we suppose a 2D curve from A to B, and on it, we distribute the sources sigma s, and the source segment ds here would produce a potential at P given as this, d phi star given as this. Here, sigma s ds is actually the strength of the source, and this is the formula for the 2D source. R is the distance from ds, the source point, to the field point P. And the total potential due to the sources distributed on the curve would be calculated as phi star given as the integral from A to B, calculated as this. Now we look at the real case. A uniform flow U0 passes a structure, but here we consider the structure it's a non-lifting body CB. That means the combination of the uniform flow and the structure will not produce any lift on the body. If we distribute the source sigma on the body surface, and this is the flow pattern we expect, combine the uniform flow and the source. So this is the flow pattern. The total potential function for the flow at P in the fluid will be given as phi equaling to phi 0 plus the closed loop integration on CB given as this. Here, phi 0 is the potential for the uniform flow. Then we have a question how we can determine the strength of the source distributed on the structure. In 2D flow, we can discretize the body surface into n small panels. See the net lines here. And here for the j's panel, the corresponding strength is sigma j. And the sources distributed on the j's panel would produce the potential function at P. It would be given as delta phi star j equaling to this. Here, sigma j is the source strength for the j's panel, and it is constant along the panel, and Sj is the length of the j's panel. Rpj is the distance from the source to the field point. Xi, yi is the coordinate on the j's panel. So based on the source distribution, we can calculate the corresponding potential at P as phi star as the summation of all these potential functions due to each panel. It would be given as this. And if we include the uniform flow, the total potential function would be given as phi equaling to phi 0 plus this term. For this example, if the uniform flow has an angle of attack alpha to the x-axis, then the potential function for the uniform flow phi 0 would be given as u0x cosine alpha plus u0y sine alpha. To build the boundary integral equation for 2D potential flow, we can use the non-penetration boundary condition. That means the normal velocity on the boundary would be 0. That is the partial differentiation of the potential function phi with regard to the normal n, it is 0. If we substitute the expression of the potential function into this expression, we would have the expression as this. It is 0 on the boundary CB, and here I equaling to 1, 2, 2, and 2n, and here Rij is the distance from the source here to the field point, the control point on the i's panel. So the distance calculated as this. Now we look at each term of the boundary integral equation. We take this term as term 1. It is calculated as u0 cosine beta I. Here beta I is the angle between the free stream direction, the dashed line, parallel to the incoming flow direction, and the normal vector Ni. Essentially, this is the expression, the component of the uniform flow on the normal direction, Ni, given as this. And for the second term here, we need to consider a case when the source and the field point are constant. That means j equaling to I. And we will have a distance Rij equaling to 0. Then we need to desingularize the expression. It would be given as this. When j equaling to I, the desingularization will be given the value for this expression as this. And the rest of the expression is given as this. J equaling to 1 to n, but j is not equaling to I. So the boundary integral equation for the 2D potential flow can be written as this. So I from 1 to n, and capital Ij is defined as this. And this is the boundary integral equation for solving the source dispute on the panels. And the simultaneous equation for serving the source strength sigma I is given as this. Here Aij equaling to half when I equaling to j, and Aij equaling to 1 over 2 pi capital Ij if I is not equaling to j. If we calculated all this coefficient and the angle beta I, then we can solve this simultaneous equation easily. Now the most important thing is how we can calculate capital Ij. Now we will have a look at an example. The uniform flow past the cylinder or past the circle, the black line. And here we will use the panel method to solve the 2D potential flow past the circle. And we use 8 panels, the net line, 1, 2, 3, 4, 5, 6, 7, 8. And the red dot are the control points. Since this is a simple potential flow, we have the theoretical solution for this. And the pressure coefficient Cp would be given as 1 minus 4 sine squared theta. Theta is the angle from x-axis, see here. And we have shown previously the boundary integral equation for 2D potential flow would be given as this. And here we have 8 panels. And in this example, I will show how we can calculate capital Ij defined as this. For this simple problem, we have the analytic solution for this integral. Now we look at the 2 panels. J's panel, this is the source panel, and the I's panel, this is the field panel. And we are interested in the control point at the center of the panel, the I's panel. The coordinates is xi, yi. So once the panel is decided by the coordinate xi, yi, and xi plus 1 and yi plus 1 decided, the control point would be decided too. And the distance Rij is calculated from the source segment dsj, the coordinates xj and yj, to the control point xi, yi, calculated as this. And the partial differentiation of Ln Rij with regard to Ni is calculated as this and given as this. Here we replace the differentiation dxi over dni by cosine beta I and dyi over dni by sine beta I. Beta I is the angle between the free stream direction and the normal direction ni. Same for beta j. And we have the relation between beta j and the capital phi j, beta I and the capital phi I. For this, we can easily see beta I is equaling to capital phi j plus half pi. And for this, beta I equaling to phi I plus half pi. See here, it's not that always. But if we write this expression beta I equaling to phi I minus 3 pi divided by 2, that means we can minus this expression by 2 pi, and the angle beta I would not change. So this expression exactly same as this. For this expression, so we have the expression for the sine beta I would be same as the cosine capital phi I. Cosine beta I is minus sine capital phi I, sine beta j equaling to cosine capital phi j, cosine beta j equaling to minus sine capital phi j. And the coordinate xj would calculated as capital Xj from the start point plus Sj times cosine capital phi j, and Yj would be equaling to capital Yj plus Sj sine capital phi j. And we can write the integral expression for capital Ij as this, and the coefficient A is defined as this, B given as this, and C is defined as this, D as this. Sj is the length of the source panel from capital Xj, capital Yj to capital Xj plus 1, capital Yj plus 1. So this is the distance for J's panel, and we have the expression for E given as square root of b minus a squared. Obviously, this integral is integrable, and we integrate this, and we have the expression for capital Ij given as this. And it should be noted here, since these two panels can be on any structures, not just on the circle. So the expression for capital Ij is correct for all 2D panels. Now the uniform flow past the cylinder can be solved by solving the simultaneous equation, this and the coefficient Aij given as this. Here, capital Ij is calculated using this formula. Then, by solving the simultaneous equation, we can obtain the source strength sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6, sigma 7, and sigma 8. After we obtain all this, we can calculate the potential at P any point in the fluid or on the boundary given as this expression. Now in this slide, we will compare the theory and the panel method for calculating the pressure coefficient Cp for the uniform flow past the cylinder. The pressure coefficient on the cylinder, the theoretical solution is given by this formula. And if we compare the pressure coefficient for the theoretical result, the dashed line, and the result from the panel method, we can see even though we use only 8 panels, the result for the pressure coefficient is very close to the theoretical result. Thus, for the flow past the circle, 8 panels may be good enough for the panel method. And for airfoils, 50 to 100 panels may be used. That's because we need to generate the fine panels at the leading edge of the airfoil. If you would like to know more information about the panel method and the example for the uniform flow past the cylinder, you can read the book The Fundamentals of Aerodynamics by J.D. Anderson. This is the 5th edition, but you can find the newer version of the book as well. In here is a summary for this panel method for 2D potential flows. By distributing sources on the 2D boundary would reproduce the flow past the structure. But in this case, there will be no lift generated on the structure. no viscous drag would be generated on the structure. For more information on the 2D panel method, we can find the good example, Xfoil. It's an open source in which to study the airfoil by distributing sources and vortices on the boundary and at the wake. The reference can be downloaded from this website. A different way developed by R. April in his book Airfoil Design and Data, published in 1990s, which is the method based on a conformal mapping of a complex zeta plane, which is a mathematical plane, into a complex z plane, which is a real plane. And we can find more different methods for dealing with the 2D panel method. In the future, I will make more talk on this. For instance, how we can use the panel method to get the lift on the airfoils.